So we have seen that for a linear time invariant system that has the form ax plus bu, at least for the state dynamics, we have that, and an initial condition x0 that is given by this scalar number. For a first order system, for first order systems, we have that the expression of x of t can be obtained by x0 plus the integral from 0 to t of the exponential of a t minus tau b u of tau in d tau. Here, in the variable u, you can put any function you want, absolutely any function you want. U of tau can be cosine of tau, can be another exponential of tau, or any other function that you want. You're going to find what x of t is going to be. Of course, this is just the state part of our system. Remember that in our state representation, we also have y, the output. So in our state representation, we also have an output equation. And the output equation is given by y equal to a function of h, t, x, and u. Now, since x of t is known for every t, thanks to the variation of Constant's formula, the determination of the output y of t is immediate. And the reason is that we have x of t, it's right here, and we just need to plug it here. So we have that y of t is going to be this function h, whatever it is. We know t, we know x of t, that is given by whatever this integral gives you, minus tau b u of tau in d tau, and then you also have your u of t. So what I'm saying is that if your system is linear and time variant in the first order because of the state dynamics in the state dynamic equation, then it doesn't matter how complicated this function h, the output function, is going to be, because you just plug it in there. However, often we have that h of t x u is time invariant and linear as well. So in that case, y of t is given by c times x of t plus d u of t. So in this case, because the function does not depend explicitly on t, depends on t because of x, or depends on t because of u, but not explicitly on t, we have that an expression like this gives us a y of t that looks very simple, because now you simply multiply, here we had I forgot an exponential of at. This becomes c exponential of at x0 plus integral from 0 till t of c exponential of a t minus tau b u of tau in the tau plus d u of t. Okay, so in this case, when the system is linear and time invariant, in the sense that both the dynamics and the output equation are linear and time invariant, it's very easy to determine the output. And however, this function h could be arbitrarily complicated. You could just plug in what you have computed for x of t and still get an explicit solution. So that's why it's important that the state dynamics is linear, and if the output equation is linear as well, well, that's icing on the cake. However, and that's also the reason why we mostly focus on the state when we have the state representation, because if we can somehow solve the system with respect to the state variable, then the output variable comes pretty much for free. So that's why we often forgot about the output when we have the state representation, and we focus on the state. What we are going to see now, at least in the case of a first order linear system, is what is the expression that we get for some specific inputs. For example, it would make sense to consider what's called a step response. So let's consider the step response. The step response in general is given by the following thing. The step response is the response of the system in the state variable or in the output variable you can have step response in the state or step response in the output, the response of the system when the input is a step function, and I'm going to define a step function in just 1 second. The step function looks like this. You have your time here, you have your input u of t. Step function is a function that is 0 up to time 0, and then at time 0 it becomes 1, or let's say more generally a capital U, and if capital U is equal to 1 we call that unitary step function. Otherwise we have a generic step function, and stays constant from time 0 till infinity, and the constant is equal to this capital U. So we can compute. Let's compute the expression of the step response for a first order system, a first order linear system. Of course, I forgot it here, but for the step response we assume that the initial condition is 0. You know that we can decouple the forced response from the free response. So since we are interested into what happens if we inject a step function into the system, let's forget about the free response. Let's just focus on the forced response. If there is an initial condition, we'll add the free response on the top of the forced response. So we have that x of t is going to be equal to exponential of at x0, but we are assuming that x0 is equal to 0, plus the integral from 0 to t of the exponential of a t minus tau u of tau in b u of tau in d tau. let's write down what u of tau is. Since we are integrating from 0 till t, in all this interval u of tau is equal to capital U. It's a constant, so we can take it out of the integral. And here we are left with the exponential of a t minus tau b in d tau. Okay, what we can do is, since we are dealing with constants, we take also b out, and we apply a change of variables, and I apply a change of variable in the following way. I call sigma t minus tau. So what happens to our integral? We have that tau goes, we're integrating with respect to tau, so tau goes from 0 till t. When tau is equal to 0, sigma is equal to t. When tau is equal to t, sigma is equal to 0. This is exponential of a sigma, and if you take d tau is equal to minus d sigma. So we take d sigma here, and we have a minus here. Let me write this in a way that it cannot be missed. So if we apply this, we get, if we apply this change of coordinates, that's what we get. So we get this minus here makes us change the integration, the two makes us switch the two integration extremes. So we are left with u capital B times integral between 0 and t of exponential of a sigma in d sigma, and now we can write this as u times b. This is given by 1 divided by sigma, sorry, 1 divided by a exponential of a sigma computed when sigma is equal to 0 and sigma is equal to t. This is what this integral is going to look like. So let's just write this in a different way for reasons that will be clear in a second. I want to take a minus sign out, and so I have to write what's inside the parentheses in this way, 1 minus exponential of at. Okay, so what we have found is the following thing, that if we inject a step into a system, a step of intensity or height u, we get a state x of t that is going to have this shape minus ub divided by a, 1 minus exponential of at. And this is the step response. This is the step response, at least in the state. One question that could be asked is the following: under what assumptions do we have that this quantity here is going to converge to a finite value? So, question: when does it happen that the step response goes to a finite value when t goes to infinity? And the answer is simple. If a is positive, then this exponential diverges, and so this definitely does not go to a finite value. If a is equal to 0, actually what we have done is not valid, because at a certain point when we have computed this integral here, we have assumed that a was different from 0. Specifically in this point we had to assume that a was different from 0 because we were dividing by a, and so the case a equal to 0, we need to analyze that in as a special case. So if a is greater than 0, then x of t diverges. If a is less than 0, let's see what happens. This exponential actually goes to 0, and so we have that then x of t converges to minus u b divided by a when t goes to infinity. We are only left with answering if a is equal to 0, this we have to solve it. We have to consider a separate case. The formula of variation of constants is still valid. The only part that is not valid is when we are integrating here. That is the following. So when a is equal to 0, I think this can be done easily because we are left here. We have u times b and this integral. So we have u times b integral from 0 to t of the exponential of a sigma in the sigma, but a is equal to 0, so this is equal to u b times t. So when a is equal to 0, a equal to 0, x of t still diverges. Okay, I hope that this answers the question in a complete way. When a is positive, x of t diverges. When a is equal to 0, x of t still diverges. The only way to have the step response not to diverge is to have a negative. So this motivates the following definition. Oh, well, at least we'll talk in the next section of this class about stability, but so far I just wanted you to understand that because we were capable of computing x of t, the step response explicitly for every a, so long as a is different from 0, we are dealing with some exponentials, and when a is equal to 0, we have this other expression. We could actually see what the behavior of the step response is according to different values of the parameter a. As we can see, the parameter b plays a very marginal role because it's just scaling the intensity of the response by a factor b.